Everybody, in this video, I am going to talk about our lesson Use Trigonometric Ratios, and we are going to start with a key idea. Trig ratios, and we're going to remind ourselves what those are in just a second, but trig ratios relate the side lengths or the sides of a right triangle, and only a right triangle, to either acute angle. Let's draw a picture of a right triangle here. And I'm going to scoot it over just a little bit. Oops. So this will be my right angle here, A, and then this point up here can be B, and then we have C. Now, I'm going to talk about these sides in relation to angle B. So angle B is going to be that theta that we are interested in. Within this triangle, though, no matter what angle, acute angle is the angle that I'm talking about, the hypotenuse is the same. So the hypotenuse here is that side BC. Now, the opposite side is the side directly across from angle B. So that would be this side, AC. That is our opposite. And then that leaves the leg that is adjacent to angle B, but not the hypotenuse. So the leg is this side. It's always so much harder when I do it that way. This side AB. This is adjacent. Now, the three trig ratios that we have, we can remember using the acronym SOHCAHTOA. And this tells me that the sine S of that angle theta is equal to the opposite side over the hypotenuse. S, or sine, is O for opposite over hypotenuse. Now, the middle part, CAH, or cosine of theta, is equal to the adjacent, A stands for adjacent, over the hypotenuse still. And lastly, TOA tells us that the tangent of that angle theta is equal to the O for opposite over the adjacent. When we're working in real world problems, oftentimes the angles that we're working with are called either the angle of elevation or the angle of depression. So the angle of elevation means the angle that something rises up. So if we have this kind of like bottom level or the ground level, the angle of elevation is the angle of increase from the ground up. From the bottom up, or the ground, or the floor up. The angle of depression, then, is from the top, or some sight line, down. So some top point down is our angle of depression. From the top down. Oftentimes this is some sight line or maybe like a plane or some high up point. And let's just make a very, very, very important note here. In these trig problems, use degree mode on your calculator. Set it to degrees. Let's look at some examples. So there is a difference between radians and degrees. We're going to look at that in a second. But right now we are just working in degrees. Example 1, we are going to find the two missing side lengths. And this one does have an image. If you cannot print it out, no worries. Just draw a quick picture of it. Let's see, it is a right triangle ABC with right angle C. And we know angle B is 28 degrees, and this side CV is 6. So the angle measure that I really know here is this angle B, this acute angle. Now, in relation to angle B, this side AC is directly opposite. The hypotenuse here is the long side AB. And that leaves the adjacent side of CB, which we know. So this is our adjacent side, which is 6 inches. Now the sides we need to find are the opposite. So I'll let that be X, and the hypotenuse. So I'll let that be Y. And we know that angle B is 28 degrees. So let's let that be our theta. And then our adjacent side is 6. So let's see, the acronym to help us with this is going to be SOHCAHTOA. And we know the adjacent side, right? I know the A. So I'm going to be working right now with either cosine or tangent. So I could use, honestly, I feel like I could probably work with either of these because the opposite, if I use the opposite and the adjacent, then I'd be using tangent. And then if I work with the adjacent and the hypotenuse, then I'd be using cosine. So I'm going to start by finding X first, which means I'm going to be using the opposite of X and my adjacent in respect to that angle B. This is our process of finding X first. So I'm going to use tangent. I'm going to say the tangent of any acute angle in a right triangle is equal to the opposite over the adjacent. So in this problem, the tangent of this angle, which is 28 degrees, is equal to the opposite side, which we don't know, that is X, over the adjacent, which is 6. Now to actually solve, to get X all by itself, I need to undo the division by multiplying both sides by 6. And when I do that, the 6's on the right will cancel. So I know that X is equal to 6 times the tangent of 28 degrees. So now I need to go into my calculator. And in Desmos, I need to make sure that I have this set to degrees, not radians. So over in the little settings option, I will click on settings and notice radians is selected. I need to toggle over to degrees. Degrees should be highlighted. And now I can type in, let me remember myself again what it was, 6 times the tangent, TAN, of 28. And since I have this set to degrees, this will tell me that 6 times the tangent of 28 is 3.1902565 blah, 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 blah. And in this example, let's round to the nearest hundredth. I kind of forgot to put that, but that's okay. And the answer we got here, x is approximately, let's go back to Desmos for just a second to see what our rounding would be. 3.19 round to the nearest hundredth. I wouldn't need anything after that. So I'm just going to write x is approximately 3.19. So let's see, I'm going to write that in the diagram here. This is about 3.19. Now to find y, I don't really want to use that length of 3.19 because that is an approximation that's been rounded. So let's just focus on the adjacent now and the hypotenuse. So adjacent and hypotenuse hints towards cosine. So I'm going to use the fact that the cosine of an acute angle in a right triangle, cosine of theta, is equal to the adjacent over the hypotenuse. So the cosine of 28 is equal to our adjacent side of 6 over the hypotenuse of, and this time actually the hypotenuse is y. So this sounds a little bit different actually to solve for y because y is in the denominator, but I don't like that. So I'm going to kind of almost neutralize this. I'm going to multiply both sides by y just to get y out of the denominator. So when I do that, the y's will cancel on the right, and I get that y times the cosine of 28, whatever that value is, equals 6. And from here, now to get y completely by itself, I just need to undo that multiplication by dividing both sides by the cosine of 28. So the cosine of 28 will cancel on both sides, and this tells me then that y is equal to 6 divided by the cosine of 28. And let's round that to the nearest hundredth in Desmos. I will type in 6 and then divided by, in the denominator, I need the cosine of 28. And let me make sure this is in degrees still. I always want to second guess because look, this is a vastly different answer when you switch to radians. So please make sure it's in degrees because we're working with degrees of an angle. It should not be ever negative. 6.79, and then right after that 9 in the hundredths, the 5 actually says, hey, bump that 79 up to an 80. So this is really like 6.8 here. Y is approximately 6.8 or 6.80. All right, number 2. Oops. A 48-inch long treadmill. I guess I don't need that. Is raised at a 10-degree angle of elevation. How high up is the treadmill raised? The nearest hundredth of an inch. Nearest hundredth. All right. So we have this treadmill that is raised up at an angle of elevation. So let's draw this treadmill. Here's my treadmill. And we know this treadmill is 48 inches long. I'm just going to say, I don't need the hyphen. It's 48 inches. And it's raised up to be perpendicular with the ground. So here's the ground, which I should maybe raise up just a little bit. And we know that it treadmill is raised perpendicularly to the ground. And the angle of elevation, meaning from the ground up, this angle here is 10 degrees. 10. And our goal is to find how high up the treadmill is raised. So I'm going to let this be h for height. So in relation to this acute angle over here in the corner, this 10-degree angle of elevation, we want to find h, which would be like the opposite side. So we want to find the opposite side, and the distance that we know, the 48 inches, is the hypotenuse. Let's see, we're going to use SOHCAHTOA. The question is, which ratio? And we know the opposite. Well, we want to find the opposite, but we do know the hypotenuse. So I'm going to use sine, and I'm going to use the fact that sine of an angle is equal to the opposite over the hypotenuse. So the sine then of 10 degrees is equal to the opposite, which we don't know, that's h, over the hypotenuse, which is 48. So I am going to solve for h by simply multiplying both sides by 48, undoing that division. And when we do that, the 48s will cancel on the right. And I know then that the height of this treadmill, how high up it is raised, is 48 times the sine of 10. Now let's see what that actually is. It should still be in degrees. So 48 times, I just use a little star, and then sine, S-I-N, of 10. Let's make sure. Perfect degrees. So it is raised up to the nearest hundredth, means I don't want anything past this 33. Now the 5 is large enough for us to round that up. So I'm going to round this to 8.34 inches. Or 8 3/34 of an inch. And this is an approximation. So 8.34 inches. Number 3. You are standing on top of a cliff, 305 meters above a lake. The angle, nope. The measurement of the angle of depression to a boat on the lake is 42 degrees. How far is the boat to the base of the cliff? So this one, definitely need a picture for. You're standing on top of this cliff. So let's kind of draw. Here's like the top of the cliff and then the edge, which I'm sure is not perfectly straight, but you know, it's about straight, and your height could be perpendicular to the ground. So it's kind of forming this almost right angle. And let's see, let's draw you up there. Yay. Okay, now the lake is all the way down here, and on our lake we have this boat. And let's see. Now, the angle of depression that you are looking down on this boat at is 42 degrees. So this is 42 degrees, and this is an angle of depression from that sight line down. We want to know how far the boat is to the base of the cliff. Oh, I'm missing how tall this cliff is. This cliff is 305 meters tall. That's going to be very helpful. Now, this does form a right triangle. We have this kind of top angle up here, this 42 degrees, and we know this 305 meters, which is really like the adjacent side that we have here next to that angle. The hypotenuse would be the distance from you to the boat, the diagonal distance across, and we are interested in from the boat, which will count this distance, to the cliff. So we are interested in this length. We'll just call it D for distance. And this side actually is the opposite side from the 42 degrees. So we are interested in finding the opposite side. We are given the adjacent. I'm going to write out the acronym SOHCAHTOA. TOA. This one doesn't involve the hypotenuse. The one that doesn't involve the hypotenuse is tangent. So the tangent of any angle theta is equal to the opposite O over the adjacent A. So the tangent of 42 degrees is equal to the opposite, which we don't know, that is the distance D we're trying to find, over the adjacent, which is the height of the cliff, 305 meters. So to actually solve for this distance, I'm simply going to multiply both sides of this equation by 305. Multiply by 305. I forgot to write how much we're going to round to, nearest hundredth of a meter. Let's go over to Desmos now. So let's see. I am going to multiply 305 times the tangent of 42 degrees. And it should still be in degrees. It is 274 point, let's round to the nearest hundredth again. I know I forgot to have us write that down. But if I'm rounding the nearest hundredth, it would be 274.62 meters. The 3 that comes after is not large enough for us to round that up. So overall, I would say 305 times the tangent of 42 is equal to that distance. So our distance is approximately 247.62 meters from the boat to the shore. We're going to do one more problem, number 4. 2 players stand on a basketball court. The angles of elevation from the feet of each player to the 10-foot tall hoop are 40 degrees and 50 degrees. How far apart are the 2 players? Or how far apart are the players? Now, without having a picture provided, we absolutely need to draw one. So that way we can kind of visualize the triangles that are going on here. So I'm going to put my basketball hoop over here. Here's like the net, little circle with the basket, and here's the post coming down. Okay, that's the more important part right there because that is at a 90-degree angle to the ground. Right? 90 degrees with the ground. And we know the post, right, is, or the hoop is 10 feet tall. So we'll just call this 10 feet. Now we have two basketball players standing, I'm sure, distances apart from the hoop. So let's see, let's make player one right here. I don't know why, okay, let's try that again. Stick person was not very good. There we go. Player one. And then we'll have player two over here. And we know the angles of elevation from the feet of each player to the hoop is 40 degrees and 50 degrees. So let's draw those and then figure out which one is which. So from the feet to the hoop would look like that, roughly, for player two. And like so, except not curved. Well, like so for player one. Now, one of these is 40, the other one is 50. So the larger angle has to be 50 degrees, the larger angle measurement. So this is 50 degrees at the base of player one, and this is 40 degrees. So we really have two right triangles here. And if you want to draw them separately, we sure could. I'm just going to draw real quick two right triangles. That's the right triangle. Just stretch your imagination. Okay, I can't get over it. There we go. Leave it like that. Here is my player two triangle. So this is 40 degrees here inside. And then this is 10 feet tall. And then player one, this is 50 degrees. This is still 10. Here's our right angle. So in both of these triangles, we know this base angle down here on the left, and we know this opposite side. The distance is to the goal is to calculate the distance between my two players, right? So really, what is the difference between the bottom two lengths of the triangle? The bottom length of the purple triangle, that's the distance from player two to the hoop. And then we have the distance from player one to the hoop. So if I subtract those two distances, I will get whatever is in between, the distance between player two and player one. But first I need to then find those two lengths. So I'm going to kind of get rid of all that. There we go. Let's start with player one. So this red triangle here. In both of these, we know the opposite, and our goal is to find this adjacent side to our angle. We don't need the hypotenuse. So if we are using SOHCAHTOA, opposite and adjacent means we will need tangent. So I'm going to start with player one. The tangent of 10 is equal to the opposite side, which is, oh, no, not the tangent of 10. That's not our angle. It's the tangent of 50 degrees that is our angle for player one. And that is equal to the opposite length, the height of the hoop, 10 over, we don't know that side, so I'm going to call this x. All right. So this is length x that we're trying to find. To find length x, first I'm going to need to multiply both sides of this equation by x. So when we do this, I get that x times the tangent of 50 equals 10. Now the x's have canceled. So I can divide both sides of this equation by the tangent of 50 to simply get x all by itself. I'm going to go over to Desmos and we will figure out what that is. We need to multiply, or sorry, divide 10 divided by the tangent of 50. And that gives us 8.3909 or so. Let's, for the sake of this, maybe so that we're a little bit more precise, let's round to the nearest thousandth. So this would be about 8.39, and looking at the 0, the 9 that comes after that would have us round that up to 391. So let's put that in our page of notes. This distance x is approximately 8.391. All right, now we need to do the same thing, but for player 2. So player 2 now, let's let this distance from player 2 to the basket be y. And I know that the tangent of 40, because that's the angle for this triangle, it's kind of hidden, it's 40 degrees. The tangent of 40 is equal to 10 over this length y, this adjacent side y that I do not know. Again, using tangent because I have the opposite of 10 and the adjacent that we don't know. Now to solve, I'm still going to multiply both sides by the variable. This time it's just y. So I have y times the tangent of 40 equals 10. And then I'll need to divide both sides by the tangent of 40. So this, in my calculator, will be very similar, except instead of 10 divided by the tangent of 50, it is 10 divided by the tangent of 40. And that is 11.917, except the 5 that comes after the 7 tells us to round it up to 8. So this says then that y is approximately 11.918. So why did we do all this? Well, we know the entire distance from player 2 to the hoop is 11.918. So if I take that distance, 11.918 approximately, and I subtract the distance from player 1 to the hoop, that distance of x, which is 8.391, this will tell me the difference between them. So 11.918 minus 8.391 gives us a difference of 3.527 feet, because that was the unit we were working with as our approximate distance between the two players. Please let me know what questions you have. This takes lots of practice. Make sure your calculator is set to degrees, not radians, and let me know how I can help you further with this.